Real quick, here's how I do ragdolls in my game. Quick disclaimer, I did not make this model myself. I ripped it off of this very old Doom 3 mod. Here's the guy that made it originally. Eventually, before I release the game, I'll either track this guy down or find a new guy to make me a new model. Background on ragdolls. Each part of the body has a bone. Each bone has a transformation as well as a parent. The reason it has a parent is because the transformation of each bone is applied hierarchically, meaning the transformation of a bone is combined with the transformation of its parent. And the parent's transform is the combination of its parent's transform, or the grandparent, and so on until you reach the root bone. This is so that when the chest moves, the arm moves with it. Because if it didn't, you'd end up with this weird warping and stretching, and it would just be a complete mess. We use the fact that each bone has a transformation to do ragdoll animations. So actually doing the physics on every bone. Let's start with the simplest case, 0 bones. You just have 2 objects in space with absolutely nothing else. They have gravity applied to them, and because gravity gets applied at the same rate, they fall in perfect sync and they never fall apart. They never drift apart. Easy, 0 bones, nothing happens. Then things get more complicated if you add something like a ledge, where now one impacts the ledge and the other one keeps going. So it kind of breaks the illusion that they're connected, if there ever was one. And then if you want to apply a constraint, say at this moment, when one impacts the ledge and another one would fall down, you then calculate where it would be after its gravity velocity is applied, and then you shift it to be no longer in violation of that constraint. But this also might violate the constraint of the collision detection, in that it might try to phase through the wall. And if you do many iterations of this, over time, it'll converge to something that's reasonable looking. I mean, except for it clipping through that corner there, but for our purposes, that kind of physics is good enough. This is how I do the arm bits that fly off of the walking guy when you kill him. So we have a way of simulating a single bone. Pretty good progress. Now, there is one problem with this, because you have only 2 points. That's only one vector in space. So you need some way of obtaining a full basis to represent the orientation of the bone. Otherwise, if you render it, it'll twist around in weird ways because it has no consistency in the rest of the orientation, the other component of the orientation in 3D. So I'll circle back to that. You then generalize it to many bones and many points. You just simulate a rigid body for each point in the skeleton and then connect them with yet more constraints for the arms, the legs, the torso, the head, the neck, etc. And we reach the same problem again that I said 5 seconds ago I said I was going to get back to, which is for each bone, it needs an orthonormal basis. And each bone only has one direction associated with it. It needs some sort of twist. It only has a swing. It needs 2 components. When I was doing research for this, I looked at the implementation for ragdolls in the original Hitman, and they're very vague. He says something about, various cross products and normalizations. Yeah, real specific for your academic paper. And a lot of bashing my head into the wall. Not literally. Eventually, I found out what he meant by this. For each bone, you specify a reference bone as well as the parent. So then you have 2 directions. And then to get the basis, you would do a projection of the reference direction onto the parent direction or the bone direction, and then take a cross product. And then now you have an orthonormal basis. 3 vectors that are orthogonal to each other to represent the orientation or the rotation of the bone, so it isn't just twisting all over the place. In code, it's very simple. It's less than 10 lines here. You have the primary direction, the reference direction, then the projection, then the cross product, and then you just throw it all in a 4x4 matrix. Now, for the application of this formula, when you first initialize the ragdoll, when the final bullet hits and you start flopping around, the first thing you want to do is get the inverse of the orientation you calculate with this formula when all the bones haven't moved an inch. This is so that you can calculate the delta by multiplying this inverse by, for each frame, you then calculate a new orientation according to the new positions of each bone. You get the delta, so it doesn't need to be, the physics orientation doesn't need to be perfectly positioned to mimic what the ragdoll was doing or what the rig was doing before the ragdoll started. And for bone 0, you just set this to be equaternion, representing no orientation. Then here, like I was saying, you calculate a new orientation, you multiply the inverse, the new orientation, and the original orientation of the bone, or the bone's rotation, the world rotation, that is, for each bone. That's a whole nother can of worms. Also, in this part of the code, there are also, in addition to distance constraints, there's angular constraints, so bones don't snap in gruesome ways or like bend backwards. Like you can't fit your arm beneath your foot. Or no, more like you can't bend your elbow backwards. That's a good example. So for each bone, you calculate where it would be if it was kinematic, or if, like the fingers, they don't have physics. They just follow the transform of the hand as if it was a normal skeletal animation. So you calculate what that would be and then use that as the axis to constrain the rotation of the physics object about that axis so it doesn't go backwards in unreasonable angles. The meat of the code, the physics simulation itself, is only a few hundred lines. The process is you compute the new position according to velocity, you add gravity or an acceleration, then you do the 3 sets of constraints, the distance constraints, the angle constraints, and then finally the rigid body physics constraints so that you don't phase through the walls of the world for the most part. That's with this simulate entity function. Overall, the solution works. The body, as you saw in the beginning, it flops around. It at least looks dead. It isn't that great of a ragdoll in that it's kind of rigid, and I had to make it that way. Otherwise, I had really weird results because this isn't a great implementation. I hacked this together over a weekend, but it's good enough for the game.